Thursday. Today our speaker is Jeff Erickson from University of Illinois Urbana-Champaign. Jeff has worked quite a lot on curves and graphs and surfaces. Today he will talk about untangling planar curves and planar graphs.
Right. Thanks, Tamal. I'll echo everyone else in saying thank you to the organizers for inviting me and for putting together this great conference. The work I'm going to talk about is joint with my PhD student, Xianqi Chang. I will, either brag or apologize in advance because I'm really going to be talking about toy problems. I'm not going to be, there's going to be no persistence, no homology, neither sheaves nor co-sheaves. It's really, everything is extremely elementary. There will be algorithms, but relatively simple ones. But this is a toy problem that I've sort of been a little bit obsessed with over the past several years, that, much to the detriment of other things. But it's cool. There's lots of interesting connections to other things. And it does, in fact, have some topology in it. But it has the most elementary topology that you can think of. In the first week of any algebraic topology course, you talk about homotopy. And in particular, I'm going to be talking about homotopy of curves in the plane. How hard is it to transform a closed curve in the plane into a simple closed curve? And of course, you all know the answer. It's trivial. You just do linear interpolation, or in this case, curve shortening flow. The question is just, you're given a curve in the plane. You want to transform it into a circle. How quickly can you do that? As a computer scientist, when you say given a curve in the plane, I have to specify what I mean by the word given. From a mathematical standpoint, well, there exists a function, and I can do linear interpolation to the function describing the circle. But in the more computational standpoint, I'm given some representation of this curve. Specifically, I really want to think of this as a planar graph where every vertex has degree 4. And when I say transform, I have to manipulate this representation, and the way that I'm going to do that is with these elementary transformations, which should look familiar if you've done anything with knots. These are sort of shadows of the classical Reidemeister moves for transforming knot diagrams. So I'll refer to as homotopy moves. And I'll name them by number of vertices before, arrow number of vertices after. So there's a classical result ultimately due to Alexander and Briggs and Reidemeister that states that any generic closed curve in the plane can be transformed into a simple closed curve by a finite sequence of these moves. But again, I'm a computer scientist. I'm not, and in particular, I study algorithms, so I'm not just interested in whether you can do it, but the question is, how quickly can you do it? How many of these moves do you need to get from the original curve to a simple closed curve? So this is problem 1. Problem 2, I'm going to go even earlier. So I know at least a couple of you have engineering backgrounds. You might have seen. Oh, I'm sorry. I should talk about previous bounds. The answer to this question, how many? There's an n-squared upper bound that morally dates back to Ernst Steinitz exactly 100 years ago. And there have been a few generalizations and improvements since then, but still this is the best upper bound that was previously published. And on the other hand, you have to get rid of the self-intersections, and so there's a linear lower bound. And so the punchline of the first punchline is that the right answer is halfway in between. You need n to the 3 halves moves. This is always sufficient, and for specific curves, this is necessary. Okay, so the second problem that I'm going to talk about dates back to, elementary physics or circuit analysis if you have a double E background. You're given a graph where the edges represent resistors, and you're given the resistances, and you want to replace this network of resistance, you can think of these two nodes, P and Q, as terminals, and this whole network acts as a resistor between P and Q. A resistor between P and Q, and you want to know what the resistance is, right? And when you first run into this as a high school student or an engineering freshman, they give you a set of tools to manipulate this graph to eventually simplify it to a single resistor. And these are simple elementary transformations in the graph. If you have any loops, you can get rid of them because there's no current going around that loop. If you have a dangling edge, you can get rid of it because there's no current going down that edge. If you have two resistors in series or in parallel, you can replace them with a single resistor. And if you have a triangle, you can replace it with a Y. If you have a Y, you can replace it with a triangle. These are known as delta Y transformations. From the perspective of planar graphs, these are nice because they come in dual pairs. The dual of a series reduction is a parallel reduction in the dual graph. The dual of a delta Y transformation is a Y delta transformation in the dual graph. From the point of view of elementary circuit analysis, there are simple formulas which date back to Arthur Kennelly in 1899 that says if I know the resistances in the original graph, then I can derive equivalent resistances in this simplified or transformed graph that are simple rational functions of the original resistances. And this is the method by which EE freshmen are taught to analyze resistor networks. So, of course, this becomes an algorithmic problem. How hard is my EE homework? How quickly can I do it? But more interestingly for me is that what really got me onto this problem was the discovery that actually you can use these same transformations for lots of other things. So in 1960, Akers showed that you can do exactly these same sets of transformations as a method for computing shortest paths. So I can replace the lengths of these edges with lengths of other edges in a way that maintains shortest path distances among the remaining vertices. And because there's a duality in planar graphs between shortest paths and maximum flows, you can just flip everything on its head, and you get a similar reduction that allows you to transform the graph down that maintains a capacity of a maximum flow. Now, you should think of these numbers not as lengths, but rather as widths or capacities. And there's a whole bunch of other stuff that people have found useful for applying these so-called electrical transformations to planar graphs. You can, if you understand something about the relationship between spanning trees and resistance, this is maybe not so surprising, but you can use these things to, given a planar graph, how many spanning trees does it have? How many perfect matchings does it have? You can do other things involving, inductors and capacitors. You can do other kinds of network reliability things. What's the likelihood that my packets are not going to get through if I remove this edge? The right way to compute this effective resistance stuff is actually to set up a linear system, but I can turn that on its head. Given a symmetric diagonally dominant linear system with a planar support graph, I can solve it using a series of these electrical transformations. Essentially, each transformation is like a constant number of Gaussian elimination pivots. And so there's lots of things that this might be a useful tool for. So, of course, the question becomes, to an algorithms person, how many such moves do you need? And in this case, it's a little bit less obvious that the answer is even finite. But again, going back 100 years to Steinitz, in fact, there is a finite upper bound. It is possible, with a finite number of these moves, to reduce any planar graph to a single vertex or to an edge between two specified terminals. And there are a few other more general results about what you can do here. Again, the existing bounds before we started working on this were an n-squared bound due to Steinitz in 1916 and a linear lower bound. You have to get rid of the edges. Okay, again, this is a slightly different list than the list you saw before, but it has the Steinitz in 1916 at the beginning. And again, the answer is exactly halfway between n and n squared. People who are playing with planar graphs already think they know how this is going to go. People who regularly play with planar graph algorithms and they see an algorithm that has a 3 halves in the exponent, they say, there's going to be a planar separator in here. No, there are not going to be any planar separators in here. Yeah. N in this case is the number of edges or the number of vertices in the planar network that you're given. Euler's formula, they're the same up to constant factors. Okay, so what was Steinitz actually doing? So Steinitz was, among other things, one of the seminal researchers in the early theory of convex polytopes. And the theorem that people like me know that's attached to his name is a characterization of which graphs can be the one skeleton of a convex polytope in R3. And what Steinitz proved is that these one skeleta are precisely the planar graphs that remain connected if you delete any two of its edges. So planar and 3 connected is the same as the skeleton of a polytope. And the way that Steinitz proved this is he said, well, here, let me take my 3 connected planar graph, apply a sequence of electrical transformations until I get down to a clique of size 4. This I can realize as a tetrahedron, and then I'm going to reverse the series of electrical transformations while maintaining the geometry. So here is a delta y transformation for one vertex of a regular dodecahedron. Replace this vertex by cutting it off with a plane. And there's similar transformations that one can do for all the other various cases that Steinitz needed to consider. Now, the way that Steinitz approached this problem was not by looking at it directly, but by introducing a tool that makes it look a little bit more topological. So this is something that we now know as the medial graph. So given this 3 connected planar graph that I want to build the polytope out of, Steinitz says, well, let's introduce a new vertex at the midpoint of every edge, and let's connect these any two medial vertices if the corresponding edges are consecutive, either around the cyclic order around one of the vertices or in cyclic order around one of the faces. And these two choices are the same. So I get this graph, and if I dim the original graph a little bit, you end up with a 4 regular planar graph. In this particular case, you got a single closed curve. That's not always going to be the case. But you'll always get something that looks like an immersion of one or more circles. So this is starting to look a little bit like something you would do with topology. And then he said, well, let's look at the effect of doing these electrical transformations on the medial graph. We get what we're calling in our paper medial electrical moves. So they look like this. So I have a vertex in the middle of every edge, and I have connections between them if they're adjacent. If I get rid of the original graphs, you get a picture that looks like this, and this looks pretty familiar, right? That's exactly the first homotopy move, and this is exactly the third homotopy move. The only difference is what happens here when you have a bigone. The homotopy move would take those 2 strands and pull them completely apart, but the corresponding medial electrical move, you just contract the bigone down to a single point. So this is why when I talked about the algorithms by Steinitz for doing homotopy simplification and doing electrical reduction, it's actually the same thing. Because what Steinitz describes as a way of doing lots of 3-to-3 moves until you can do one of these to reduce the number of vertices. And at that point, it doesn't really matter whether you're doing 2-to-1 or 2-to-0. Okay, so what did Steinitz do? One of the key observations in Steinitz's proof is that if you look at any 4 regular planar graph, the medial graph of something planar or just a curve, either you can find an empty loop, which you can get rid of with the type 1 move, or you can find what he calls a minimal bigone. So a bigone is a disk that's bounded by 2 interior disjoint simple subpaths in this graph. And a minimal bigone is a bigone that doesn't contain another bigone. This is inclusion minimal. Or in the language of the original paper, this is a spindle, and this is an irreducible spindle. And then he also observes that inside any minimal bygone, in English, inside any minimal bygone, you can find at least two triangles. And moreover, at least one triangle incident to each side of the bygone. And so what that means is that I can reduce the bygone. I can reduce the number of faces of the bygone by doing a type 3 move, which is either going to be on the side of the bygone or it's going to be on the end of the bygone, right? And so if I have a bygone that has 42 faces inside it, I can empty it with 41 of these moves, and then the last move I can either contract or delete the thing. So here's the algorithm that is implicit in Steinitz's proof of Steinitz's theorem. If there are vertices left to get rid of, look for empty loops. If you don't find an empty loop, look for a minimal bygone, clear it out, and then delete it. Okay. And because clearing out a single bygone, you have to remove at most n faces. Each bygone requires a linear number of moves, and so you get a quadratic upper bound overall. Okay, yeah. So the three connectivity comes in Steinitz's proof. You never have loops, and you may create, when you get rid of one bygone, you may immediately create other empty bygones. You just get rid of them immediately, and then you have three connectivity back again. Okay. Now, 75 years later, people started actually looking at electrical reductions again. And so they developed a different algorithm which has some nice properties. So this is by Feo and Provan, published in 1993, but much of the work was done in the mid-'80s. What they observed was that if you number the faces of your four regular plane graph by their depth, so the depth of this face is 4 because any path from this face to the outside has to cross the curve at least 4 times. So this is kind of an undirected, unsigned version of winding number, right? And then you can think of the sum of all these face depths as a potential function, as a score for the curve, which is intuitively, the more complicated the curve is, the higher the score is going to be. And what they proved by an incredibly convoluted, opaque case analysis is you can always find either an empty loop, an empty bygone, or some triangle where if you do the corresponding triangle move, the potential will go down. And specifically, the depth of the face that you remove is going to be bigger than the face of the depth that the face that you introduce, and all of the other depths will either stay the same or possibly go down. Okay. And so this leads to another algorithm that can do this reduction in n-squared moves, which is if you find empty loops, get rid of them. If you find empty bygones, get rid of them. Otherwise, find a positive 3-to-3 move, something that reduces potential. And because every single move reduces the potential of the curve, the total number of moves can't be more than the original potential, which is at most n squared. Okay? So that's what was known as of 20 years ago and as of 100 years ago. What are we going to do that's new? So we're going to use features of both of these algorithms. On the one hand, we're going to use the sort of, let's find something and locally reduce it. And on the other hand, we're going to analyze it in terms of Feo and Provan's potential algorithm. So the basic algorithm is really a very, very slight variant of Steinitz's algorithm. And I really should have put up here that essentially this algorithm was previously used by George Francis in the late 60s and early 70s to prove what he called the folded ribbon theorem. So instead of looking for bygones and removing them, I'm going to look for loops, which is actually quite a bit simpler. Just wander around the curve until you reach a point the first point that you've seen before. That subpath is a loop. And so I'm going to take this loop and I'm going to contract it. And the number of moves that I need to contract it turns out to only be 3 times the number of faces, the area of the loop. And the way that you contract it is if there's a bygone on the boundary of the loop, fine, get rid of it. And if that's not enough to make the loop empty, then there must be a vertex that has a neighbor on the boundary of the loop. And so I'm going to drag the loop over that vertex to move the vertex outside. That requires two moves. One 0 to 2 move to introduce this outer bygone, and then a type 3 move to move the vertex outside. Yeah?
You were assuming 4 regular.
Yes, I'm assuming this is a curve in the plane. We're doing homotopy here. So it's 4 regular. I'm assuming genericity. There are no triple intersections. There are no pairwise tangencies. There's no space-filling nonsense. It's just a... So if the cases look like this, if the loop is empty, just remove it. If the loop contains any interior vertices, it must contain one that has a neighbor on the boundary. If the loop doesn't contain any interior vertices, then it must have a bygone on the boundary. So, okay. Moreover, if you do this contraction, the potential drops by at least the number of faces in the original loop, because every face in the original loop is now not inside that closed curve that used to be there. So whatever the best path out of that loop used to be, it now crosses the curve one less time. Now the potential might actually drop further. You'll notice that like this face with depth 4 now only has depth 2. So there might be other places where the depth goes down, but at a minimum, every face in the original loop has its depth drop by 1, and so the total potential drop is at least the area. Okay, and so, yeah, this leads us to another quadratic time algorithm, but that's not really why we did this. The reason we wanted to do this is we needed another tool that was relatively simple and easy to understand to get a handle on this potential. And the big problem with the potential argument is that the potential of the whole curve could be quadratic. There are examples of curves where there are faces of linear depth, and there are a linear number of them, and so you've a quadratic potential. So what we're going to do instead is we're going to apply a kind of local version of this algorithm. We're going to focus in on a small piece of the curve where we can locally define potential as something much smaller than the potential of the entire curve. We locally improve within that smaller region, and then recursively simplify everything else. And now, again, the people who are used to playing with planar graphs think, see, I told you there'd be a planar separator in there. But no, not a planar separator. So this thing that we're extracting out, we're borrowing from the knot theory literature. We're calling this a tangle. So normally, knot theorists refer to a tangle as either the intersection of a knot diagram with a disk or the intersection of the knot itself with a ball. This is sort of, a shadow of that. You can think of a tangle as a disk with a bunch of generically immersed boundary-to-boundary paths, which we'll refer to as strands. And we can define the depth of a face and the potential of the tangle exactly as we would for curves. So thinking of the outer boundary of the face as part of the tangle, so the boundary faces all have depth 1, and the depth goes up as we go in. So what sort of the most technical part of our homotopy algorithm is this bizarre lemma. It's got a lot of parameters flying around, but the algorithm itself is relatively simple. We can take any tangle and tighten it, meaning we can homotope it into a position with a minimum number of intersections in time that depends on the number of vertices in the interior and the maximum depth and the number of strands. So the basic idea is the first thing we do is we remove loops exactly the way that I described earlier. And because every time we remove loops, we're reducing the potential by at least a third of the number of moves. The total time to remove all the loops is at most the potential, which is at most the number of vertices times the maximum depth. And then we need to straighten out the strands. This we can do basically using the same idea. in time proportional to the number of strands times the number of vertices. So going from here to here, I'm just contracting loops one at a time to get rid of these excess intersections. The idea is I pick out a particular strand and I move it as far to the side as I can to make sure that this strand doesn't have any excess intersections on it. And the number of moves that I need is proportional to the number of faces inside this region. And then I just recurse on the smaller tangle. Okay, so this is kind of complicated, but it'll come around and simplify in a couple of slides. So why do we want to do this? The reason we want to do this is because it's possible to find tangles that are useful in the sense that, that one of those 1/2 should be a 3/2. In the sense that the overall time simplifies down to just the number of vertices to the 3/2. And moreover, when I do this recursion, I make a significant amount of progress. I delete at least half of the vertices inside the tangle. And so I can somehow charge the work that I did to the vertices that I removed in a way that leads to an end of the 3/2 running time. So what properties do we need? The first thing we need is that the number of interior vertices is at least the square of the number of strands. You can think of this as a kind of isoparametric inequality. We want the area to be at least the square of the perimeter. But the constants here actually matter. If the tangle were tight, every pair of strands intersects at most once. The number of intersections would be s choose 2, which is about half of n squared. So by insisting that m is at least n squared, that means when I'm done tightening, I've removed a majority of the vertices. And the second thing is that I also want the maximum depth of the tangle to be small. And then using the algorithm from the previous slide here, that means I can plug in d is square root of m and s is square root of m, and this whole thing simplifies down to just m to the 3/2. And these things always exist, and there's a simple algorithm which I won't spend much time on, which you look at sequences, essentially depth contours. You find the depth contours that contain some point with maximum depth. This gives you a sequence of nested tangles, and one of them is useful by a counting argument. Okay, so putting this all together, as long as there are any vertices, I look for a useful tangle, and then I tighten it using the algorithm that I just described. Remove the loops, and then pull the strands taut. Tightening a useful tangle requires m to the 3/2 moves. So for every vertex that I removed, I can charge a square root of n moves. So every vertex in the entire curve gets charged square root of n moves, and so the total number of moves is only n to the 3/2. Okay? Pause. Those of you who are not used to charging arguments can wake up now. We're going to do some math. Okay. Why should I believe that n to the 3/2 is the right answer? So for this, we're going to defer to a curve invariant that was defined by Vladimir Arnold and Francesca Aicardi in the early 90s. So curve invariants are very much like knot invariants. It's a numerical quantity that you attach to the curve that if the two curves have different invariants, then you know they're not ambient isotopic. In this case, the invariant was defined somewhat indirectly, saying the defect of a simple closed curve is 0, and the defect changes when I do a homotopy move according to various cases. So a type 1 move doesn't change the defect at all. A type 2 move either doesn't change the defect or reduces it by 2, depending on how those two strands are connected. And a type 3 move either increases by 2 or decreases by 2, again, depending on how those three strands are connected by the rest of the curve. It's in no way obvious that such an invariant exists. except that there's a closed form formula that was discovered later. But it immediately gives you a way of bounding the number of moves, because every move changes the defect by at most 2, and I want to end with something where the defect is 0. If you want to think about intuition, think of this as essentially a signed version of the potential we were using earlier. Intuitively, you can think of this as like the sum of the winding numbers of all the faces. That's not exactly what it is, but it morally, for purposes of intuition, that's how you can think of it. And so we have something that we can use to lower bound the number of homotopy moves that we need to do. We have examples of curves where the defect is big. And so this gives us the lower bound. And specifically, the bad examples are standard projections of standard torus knots. So we just take these things that you might get out of a spirograph. The flat torus knot TPQ winds around the origin P times and oscillates back and forth between inside and outside Q times. Okay. So by carefully describing a specific algorithm to simplify these things and watching how the defect changes, we derive some general results about the defects of these curves. The specific examples I think that are interesting here is if Q is equal to P plus 1, then we have an exact answer. The defect is 2 times P plus 1 choose 3. This is about n to the 3 halves over 12. Okay. And this specific example was actually, or something very close to this example, was previously used by Evan Zohar and Joel Haas and a few other people for investigating invariance of random knots. So specifically, they were thinking of a model where you have a curve and you resolve each of these intersections into an overcrossing or an undercrossing independently with probability 1/2, and ask, well, this gives you a random distribution of knots. What's the distribution of various finite type invariants? And this shows up in the calculation of the simplest such invariant. If I flip the parameters, so the P is 1 bigger than Q, then in fact I get negative defect. Again, remember defect is signed. So I get something that goes down to minus n to the 3 halves times a constant. And this also showed up in a paper by Hayashi et al., who, for completely different reasons, were looking at trying to bound the number of Reidemeister moves for simplifying a particular family of knot diagrams. So you get these defects that vary wildly, but in the extremes, they can go from positive n to the 3 halves to negative n to the 3 halves. Interestingly, the global behavior of these things is really not very nice. We have essentially an algorithm that can compute the defect of one of these curves that looks like Euclid's GCD algorithm, which applies, among other things, you can have really complicated looking curves where it's clear that these things are going to take n to the 3 halves moves to simplify. But if I take, say, consecutive Fibonacci numbers as my parameter, the defect actually turns out to only be linear. So this defect is not a tight bound on the number of moves that you need. It's just good enough to give us a worst case bound of n to the 3 halves. Okay, so that's what I want to say about homotopy for the moment. This might be a good time to stop and ask for questions. Yeah, Herbert. The behavior of the sum of winding numbers is not quite as nice under homotopy moves. And so it's actually rather, the choice of invariance is actually rather delicate, because we need to make sure that whatever homotopy move we make, the effect on the invariant is only going to be plus or minus a constant. Otherwise, the lower bounds just don't work. Yeah?
So you said that looking at these, it seems clear you need at least 3 halves. There's no other lower bound.
I'm stating a personal belief. I'm not stating a theorem. Yeah?
Have you done anything on other surfaces?
Yes. Unfortunately, I don't have a slide here. For other surfaces, there are 3 cases to think about. One is the curve is contractible. In that case, we still have an n to the 3 halves lower bound, but the only upper bound we have is n squared. So Haas and Scott prove that if you have a non-simple but contractible curve, it's got a bygone in it. So Steinitz's algorithm works in n squared time. The second case is it's not contractible, but you can simplify it down to a simple curve. It's homotopic to an embedding. In that case, Haas and Scott's algorithm still works in n squared time, and we have a family of curves that have quadratic defect. And so in that case, we know the answer is n squared. In the third case, we just have a curve, and we want to simplify it as much as possible. So we still have an n squared lower bound, and it's known by various curve shortening techniques that you can get from any curve to any other homotopic curve with a finite number of moves. And that's essentially the strongest result that's known. We don't even have, I think you can turn that into a polynomial, an exponential upper bound, because you can reduce to minimum position without ever increasing the number of vertices. And there are only so many 4 regular graphs on the surface with a certain number of vertices. But we don't even have a polynomial upper bound for that case. Any other questions?
So does it work for any surface, the oriented surface of any genus?
Any orientable surface of any genus. Non-orientable surfaces, things are a bit uglier. Okay, so now let me switch back to the other problem. So there's when I talked about Steinitz technique, I said, oh, well, there's this connection between electrical moves and homotopy moves by way of the medial graph. We can think about medial electrical moves in sort of the same breath as we can think about homotopy moves, except we have to remember this weird difference in between in the type 2 move. So let me formalize that. All right, so let me actually draw the connection more formally. That says the electrical problem is formally harder. And the way that I'm going to do that is first by reasoning about when you either delete or contract edges in the original network that you're trying to simplify, not in the medial graph. So I'm considering what the difference between the difficulty in reducing the original graph and the difficulty in reducing any minor, that is anything I get by either deleting or contracting edges. But I want to view this through the lens of medial graphs, so I look at what effect deletion and contraction have on the medial graph, and this turns out to be just smoothing the vertex. This is completely symmetric because the dual of deletion is contraction, and the dual of contraction is deletion. This is essentially the most elementary version of Poincare duality that you can possibly imagine. So smoothing. And the reason we want to do this is there's this nice lemma that says reducing any proper minor of a graph requires strictly fewer moves than reducing the original graph. So by contracting or deleting an edge, you are reducing, not less than or equal to. This is a strict inequality. You need fewer electrical moves to reduce the resulting minor. And the proof which we have in our archive preprint basically says, well, there are only a few cases that I have to consider. Look at the first move in the minimum sequence of electrical moves for G, and then I need to smooth some vertex of the medial graph. And depending on what the move is and the way that I smooth, I'm either going to end up with a parallel, slightly different electrical move or something that I don't have to do anything. And then the rest of the proof just proceeds by induction. Okay. I just wanted to show off this pretty picture. All right, so why do I care about these minors? Because this allows me to prove this formal connection that says the minimum number of electrical moves I need to reduce a graph is at least the minimum number of homotopy moves that I need to reduce its medial graph. And the proof is really simple. Whenever you run into a 2-to-1 move, replace it with a 2-to-the-0 move and recurse on the resulting minor. Okay. So this means that the lower bound that we proved for homotopy moves immediately gives us an n⁻³ lower bound for electrical moves. And in particular, for the anti-medial graph, the Tate graph of the flat torus knot is a cylindrical grid. So if I take a k by 2k plus 1 minus 1 cylindrical grid, here with k equals 4, its medial graph is a torus knot, and we already know this needs n to the 3 halves homotopy moves, and therefore this needs n to the 3 halves electrical moves. So if you want to be mean to your EE 101 students, you can ask them, here's your graph, go. And they're going to be spending a long time figuring out the effective resistance with that graph. Okay, so that's the lower bound side. In the last few minutes of the talk, I do want to say a few words about the upper bound for electrical moves. The algorithm here is a bit more complicated, and it's work in progress. So this may yet be simplified, or we may find more bugs than we found already. So at some level, you should think of what I'm going to say for the next few slides as preliminary bits of intuition. There's not really going to be time to talk about technical details, and given the novelty of the technique, you shouldn't believe the technical details anyway. But I'm reasonably confident that this works, so I'm going to show it off anyway. So how would we'd like to leverage the homotopy algorithm to do electrical reduction. Unfortunately, the thing we just saw shows that we're trying to reduce the wrong way. I can take any electrical reduction algorithm and turn it into a homotopy reduction algorithm that's faster, but I can't go the other way, and in particular for the algorithm that we developed where we're shrinking down loops, we can't leverage that directly to produce an electrical reduction algorithm because the algorithm requires these moves where I introduce vertices using a type 2 move. And there's no electrical equivalent of introducing a bygone. So at some level, we have to sort of step back and say, well, what should we do? So one thing that we thought is, there's this Feo and Probon result that says in any closed curve, and in fact, any 4 regular planar graph, there's always a positive 3 to 3 move. Maybe this also applies to tangles. If it did, then we could use essentially the same charging arguments to derive an n to the 3 halves move algorithm. Unfortunately, this isn't true. There are tangles where there are no positive moves. Okay, sorry, that didn't work. Another possibility is to go all the way back to Steinitz and say, let's look for a bygone, but maybe we can always find a bygone where the area is small. If we could always find a bygone where the number of internal faces was square root of n, then we'd spend square root of n time getting rid of that one vertex, and that comes out to n to the 3 halves. Unfortunately, and this took us a bit of time, this conjecture is also false. And here's the example. This is a nice picture I call the Fibonacci cube. So take a regular square grid and lay down a sublattice of the dual lattice here, where the slope of this line is a ratio between 2 consecutive Fibonacci numbers. So I think this is the 8-5 Fibonacci grid. And then tile the 6 sides of a cube with that pattern, and the lines all match up because you're doing things on a lattice. This graph is 4 regular, and most of the faces are squares, except at the corners of the cube where you've got 8 triangles. Every bygone in this graph has a linear number of faces. So here's a bygone. Here's one corner, and you go off to the top, and that folds around to the bottom. Here's the opposite corner. It folds and joins up here. This is big because I started far away from the corners. The bygone's going to be fat. I'm going to use up most of the vertices of one face. If I start a little bit closer to the corner, I get another bygone that's thinner, but the nice thing about the Fibonacci lattice is you can go a long way before you hit another lattice point. And so these thin bygones tend to reach very long. And so by grinding through the cases, one can show that every bigon, in fact, contains at least 1/12 of the faces of the cube. All right, so this is an interesting bad example because if you gave this, or this is the medial graph of the thing that you would give your students, not only would it take them a long time to finish, but it would take them a lot of at least a linear number of 3-to-3 moves before they could even start getting rid of anything. So it's going to take you forever to finish, and it's even going to take you forever to get started. But what we can do is we can find minimal bigons with small perimeter, or at least under some circumstances. And by being a little bit more, careful about how we reduce bigons with small perimeter, we can do this in a way where some part of the reduction process we can charge to a drop in potential, the way Feo and Provan do it, and some part of the reduction process we can charge directly to the number of faces that we remove, the way we might with Steinitz. And so we get an algorithm that looks like this. Find a useful tangle. Inside that tangle, find a small perimeter minimal bigon. Shrink it down to a centipede as a minimal bigon with no interior vertices. Then shrink it down to the centipede down to something empty, and then remove that. And then there's a complicated charging argument that ends up giving you an upper bound of n to the 3 halves. Okay, let it wash over you. Okay. So let me finish up by mentioning a few open questions. Somebody already mentioned the case of doing homotopy for curves on other surfaces. I think the biggest open question there is just, can you get from one curve to another homotopic curve using a polynomial number of moves? It'd be nice to go for n squared, but I think just n to the 50th would be a good start. On the electrical side, we have an algorithm that runs an n to the 3 halves moves, but we don't know how to find those moves quickly, which means we can't actually use this as a tool for any of those other things that I talked about at the beginning of the talk yet. The other bottleneck is all of those results, or most of those results, require the reduction to maintain a couple of special vertices called terminals. I need to know the resistance between P and Q, so I can't execute any electrical moves that delete P and Q. So we need to extend the algorithm to planar graphs with terminals. And then there's some interesting questions about other families of graphs that can be reduced that aren't necessarily planar. But the most important question is, even if we do all this, even if we come up with the right algorithms, I know this is a dangerous question to ask in a room full of mathematicians, but I am a computer scientist. Is this stuff, in fact, actually useful? Would this actually lead to faster algorithms for doing something with planar graphs? And at some level, this is the real motivation for all this stuff. There's lots of useful algorithmic techniques that have been used for planar graphs. I mentioned separators. There's several others. But there's a sense among the planar algorithms community that we're hitting the limit of what we know how to do with the tools that we have. And so I'm proposing this as, I don't know if this is going to work, but at least it's different than anything that we've done before. So maybe people will find useful things to do with it, or maybe it's just a fun toy problem. And with that, I'll finish. Thank you.
The problem is as difficult on a sphere with finite punctured points.
So that's, in fact, equivalent to the problem with electrical reduction with terminals. Right, so you have this, again, you look at the medial graph, and you can sort of think about homotoping things in the medial graph, except for weirdness with bigons. Those terminals turn into faces that you're not allowed to contract, which is the same as having punctures. So in some sense, the question, how quickly can you reduce curves on more complicated surfaces, and how quickly can you electrically reduce graphs with multiple terminals, are the same question, or at least very closely related questions. What's known now, for example, is translating into homotopy. You can homotope between two equivalent curves on a pair of pants, 3 punctures, with at most n cubed moves. But we think that really ought to be n squared or maybe even n to the 3/2. Yeah.
So does this also imply an approximation algorithm for any of these parameters?
That is an excellent question, and I don't know. Probably. I mean, there are interesting. I mean, there are interesting connections between this and so multi-commodity flow when you have terminals on the boundary of a planar graph. So the Okamura-Seymour theorem gives you a factor 2 approximation, or lets you route with a congestion of 2. You can do the same thing with these moves. So it's possible that you can sort of generalize the same kind of things that Okamura-Seymour was used for through this lens to get other approximation algorithms. But we haven't poked in that direction seriously. Yeah.
So a lot of the lower bound examples were either kind of like grids or like products of simple graphs.
Yeah.
And so in those cases, do you know how to find the moves for the electrical case?
In those cases, the reduction algorithms are very simple because you've got this very regular structure. And so, in fact, the way we prove that the defect is n to the 3/2 is by describing a sequence of n to the 3/2 moves to reduce it. But, I mean, this is familiar for people who are used to thinking about planar graphs and graph minors. Morally, every planar graph is a big grid. So if you can work things for grids, then you're halfway home.
There is no other question. Let's thank
Okay.
Jay for
Thanks again.